Hi Mohan, can you hear me? Hello? The volume is a bit, I don't know if you're trying to.
Hi, Varsha.
Hi, I can hear you well. Thank you. So yes, I would just request you to just share your screen for a second.
Yeah.
Now, if you scroll, like once you, are you able to share your screen?
Varsha, your voice was not clear. Can you come again?
Oh, I'm asking, can you please share your screen for a few seconds?
Okay, ठीक है. Okay, I'll do it.
Yes, thank you. If you can scroll on top, there'll be more options there.
No, this is not from my end. I think somebody else is sharing, I guess.
Oh, Manisha. Thank you, Manisha, but not now. Yes, can you share now?
Yeah, I'll do it.
Yes, great. If you can scroll on top, you'll see more options or just more written.
Okay.
Yes, if you click on more, there'll be disable participants annotation.
Okay.
Have you clicked it?
Yeah, I made it.
Okay, great. Yes, thank you. I'll just give me a second. I will start by introducing you and then we can move forward from there.
Okay.
Yes. So, welcome everyone. Thank you for joining us in the morning and having a wonderful start of a Saturday. So, yes, do we wish to wait for more people to join? Then, if everybody can hear me, firstly, please write a yes on the chat box. Thank you, Daniel, Manisha. Thank you. Yes. Can we wait for another 2 minutes or so? Okay. Hello, everyone. I'd request everyone to not share their video. Okay. We are about to start. Thank you for joining us. So, yes. So the session for today is Introduction to CNN, and we have Mohan Raj, who is helping us understand the whole topic for the day. So Mohan Raj is a data scientist and has an overall experience of 6 years in machine learning, computer vision, deep learning, image processing, and video analytics. Now he's completed his PhD in the area of computer vision, video analytics, and deep learning from Madras Institute of Technology. He has developed a lot of solutions for face detection, face liveness detection, future extraction for face recognition as well. Also, he has mentored or taught a lot of students in the same field as well. So, welcoming Mohan to give this awesome session, and I hope everybody enjoys it. I would request everyone to use the chat option wisely, and also I'll be sharing a feedback form in the beginning and at the end. So please make sure you fill it and give us your views on it. So yes, thank you so much. Over to you, Mohan. Please go ahead and have an awesome session.
Thanks, Osha.
You're welcome.
Hello, everyone. So very good morning. The agenda for today's session, I'll start with the what is computer vision and what is the need for deep learning, and I'll talk about neural networks and CNN, and then a few applications of CNN for image classification and object detection and segmentation. But I'll use Colab for the Ansan session, which is an Google provided GPU instance. So where I'll walk through the code for the CNN as well as the neural network. So if you have any questions, as Varsha mentioned, please post it on the chat box. So I'll respond as soon as possible, or else I'll take it at the end. So quickly, I'll just give an overview about the computer vision and then machine learning, and then I'll take about what is neural networks and CNN. What is a machine learning? Basically, it is learning from the experience with respect to some task. And then we are trying to predict the feature, what it will be the data. For example, when I say the face recognitions, right? Everybody are using mobile phone with the registered face images. And when it comes to a next time, it says that the person is X and Y, right? And also we are trying to everybody are using a Gmail, right? We'll be having the general and Facebook, social media, right? So how does that work? That is also comes under a machine learning, right? So earlier, most of the datas are labeled with which are the mailboxes are spam and which are the mailboxes are general and which are the mailboxes are social. So based on that learning experience, it is capable of predicting what will be the future or upcoming data. So it's basically learning from the experience. The traditional approaches, what we do, for example, somebody is running, right? So based on the speed, we are trying to make a prediction saying that whether the person is walking or whether the person is running, whether the person is what kind of action is doing. Basically, it is from the rules. So we'll give you the input data and the rules, and we are trying to predict the output. But in case of machine learning and deep learning, what we are trying to do, we are given with the input and we are given with the output. So we are trying to make the rules out of it. So the learning happens, what kind of rules we can extract out of the data. So based on that, we can make a predictions of what kind of output data it is. So some of the applications I just wanted to highlight. These are some of the applications which is developed by the companies like Google, Amazon. So here, what happens? The Google Lens, where if you show some of the sample images like flower species, it is capable of detecting what the flower species. And also the several applications like if you are in front of the hotels, right? So if you want to know what is the rating and the feedback, just click a pictures and it will give you the information about all those history, right? And then the Amazon GoPro, it is an walkout technology. The current situation in the supermarket, what happens? So you just go into the store and you will pick it up what are the items which are required, and then you will stand in a queue, right, for the billing, right? But what they made, you need not to wait for the billing. Just take the product. They used a sensor fusion and computer vision and deep learning technology. They will track you what are the items which are picked up. It will be added into an e-wallet, and then the money will be detected. And then the third one, which is an advanced driving assistance system. like traffic sign detections and the lane detection and collisions, and then free space. So when there is autonomous vehicles, right? So we have to detect what happens on the road scenario. So these are the some of the application, the current applications many of these industries are focusing on. So when I say mission has to understand, right? So how do you represent any image or video or any input data? For example, when you take an apple, right? So what comes to in your mind? Basically, apple looks like a fruits, right? Some people will think that it's in fruits, but there are chances apple iPhones also there, right? But as an human being, by looking at the image sample, we are trying to capture the uh, some of the features like color and then shape and then texture. Our human eye is capable of distinguishing what each object it is, right? But how do you represent the image to one machines, right? That comes to one, because machine will looks like a 2D array with the n number of pixels in the rows and n number of pixels in the columns. By storing all those pixel value to one machine, is that can understand which is Apple iPhone and which image is Apple fruits. So there is a gap between how we perceive an images and then machine representation. So you can see there are two images on the left hand side and then right hand side. In the left hand side, the image which looks like a apple fruit, right? But as a human being, right? But when we represent, as I mentioned, it is a 2D array with n number of pixels in the rows and n number of pixels in the columns. So the each pixel values are between 0 to 255. So the 0 represents the black and 255 represents the white pixels. Then we'll have a great shades of pixel values between the 0 to 255. So when I say it is a grayscale image, it will have a one-dimensional array, 1D array, which has the single channel. If it's a color images where we'll have a red, green, and blue channel, we'll have a three matrices, a three color component. For each pixel, we'll have a red channel, green channel, and then blue channel. But each matrix, the values are between 0 to 255. So now we have two images, which are Apple fruits and then Apple iPhone. So the each images, if you compare both the images, but more or less it looks similar with the pixel value. But how the machine can distinguish, how the machine can learn by providing this kind of sample. So there is a gap between how we perceive as a human being, how we perceive an information from the images, and then machine representation. So we'll call it a semantic gap. So to fill this semantic gap, basically, instead of storing the raw pixel intensity value, we'll go for an feature extraction technique. There is a feature engineering technique. From the input matrix, can we get the color descriptor, which may be a mean or standard deviation, or it may be a krutisys, or it may be skewness, or can we get some texture pattern out of the input matrix, or can we get the shape feature descriptor. So feature engineering, nothing but it is some numerical value. It may be n-dimensional numerical value. So where we'll say the machines, those numerical values are unique or distinguished between the two different images. In this case, Apple iPhone and then Apple fruits. So that there is a common or unique feature between the Apple iPhone and then Apple fruits, so that the machine can distinguish when we give the some unknown data, it is capable of classifying what kind of data it is. So once we have this feature value, then we'll go for, these are the other feature engineering technique. These are the color channel feature descriptor, histogram, and texture, and HOG, and then key point feature. These are the some of the computer vision and graph feature technique. So and graph feature engineering technique, it's basically it is an application dependent. But in case of deep learning, with irrespective of the application, we can reuse the same features. But in this case, for example, I'm going to extract a color features, right, for this apple, right? But can I use this color feature to classify the shirt pattern? Basically, I have a checked pattern and I have a plain shirt, and then I have a striped one. So is that color will help to classify what kind of pattern it is. So we cannot reuse that color feature to classify the pattern of shirt. So in this case, the traditional pattern recognition or feature engineering techniques are application dependent. So we cannot reuse the same feature engineering technique for the other applications at all. But in case of deep learning, where the same features can be reused for a number of applications. So I'll discuss in the upcoming the slides. So what are the challenges will be when you go for a feature engineering technique, or when you want to do an image classification or object detection or segmentation? So these are some of the common challenges as to be considered when we build on computer vision applications. So in this case, we can see that there is a dog image and the backgrounds are very complex in nature. So how can our machine can do a classification? Because there are more the distributions in the backgrounds are there is a gross, right? So how can machine can do a robust classifications? There is a complex background in these images, but what we can do, we can have a crop only the region which has the dog and then eliminate the remaining portions. So you need to extract the foreground and background separately, and then you extract the foreground alone and then give it to a image classification or a deep learning based classification algorithm. So the next one, for example, most of them we are trying to take a pictures, right? In a real-time situations, right? When you consider an airport or railway stations, right? There will be CCTV camera will be placed several places, which may be a top-mounted camera, or it may be side-faced camera, or it may be frontal-faced camera, right? So this is the board which we call it as a Raspberry Pi board, which is an IoT device board where we can run these computer vision and deep learning applications on this board. So the image I have taken here, which capture the images and the different angle and then orientation. In this case, 45 degrees, 0 degree, 90. So we need to collect the samples of the same images and the different angle, so that when we give a sample or core image or a test data, the machine will have a capability of classifying what the core data it is. So the next one, it's a challenge is the scale variations, right? So when we capture an images, right, the object between the distance between the objects and the camera. For example, I'm trying to capture a pictures, right? I'm very close to the face. Then the face image looks very bigger, right? And the person is very far away from the camera, and I'm trying to take a pictures, right? The objects look smaller. Though the different scales of object, it is a coffee cup or some kind of cup. It is taken on the distance, the different distance between the objects and the camera. So it looks like a different objects, right? In the scale, right? But though it is the same object, but it looks different in the scales, right? But the machine learning or computer vision algorithm has to classify it as a coffee cup, but the scales are it is a different. Coming back to one, the next challenges is an occlusions, right? So when you place any camera in the real-time situations, right, railway station or airport or public bus stand, right? So those scenarios, there will be multiple persons will be walking in or around, right? There will be one person will be occluded with the other person. One real-time example, when in a classroom, right? There will be multiple chairs will be there. The person who is sitting at the front, right? It will be visible, fully visible to the camera, but the next person behind the others will be, it will be partially occluded by the camera. So though it is a partially occluded, right? So how can our machine learning algorithm will classify efficiently? So in this case, on the left hand side, we also have a dog, and the right hand side also we have a dog, right? But on the left hand side, where we have a fully visible, the computer vision algorithm can extract the features robustly. But we have a on the right hand side where we have a only partially visible component to extract and features. So how efficiently our machine learning or computer vision algorithm can classify such kind of objects. So coming back to one next challenges. So these are common challenges in case of computer vision application. So everyone, when you take a pictures, you look at the shadow and then lighting, whether we have a proper lighting conditions, right? Though you can see the image on the left hand side where it has taken on the proper lighting condition, and the image on the right hand side which is a dark lighting conditions, right? Though it is the same object, but it is taken on the different lighting condition. For example, I'm just building a face recognition applications, right? I registered my faces within the indoor environment, right? and then I go back and outdoor environment, if I click pictures, and it has to say it is a movement, right? So that are the simple example. So when you build a computer vision applications, right? So I have mentioned few challenges. So how far the computer vision application can overcome such a challenges when you build a object classification, or it may be object detection, or it may be object image segmentations algorithm. So once we extracted the features, the next step would be the machine learning algorithm, right? Whether it may be supervised or it may be unsupervised and semi-supervised. So quickly, I'll walk through what is a supervised and unsupervised semi-supervised algorithm. So in this case, supervised algorithm, when I say images, right? I want to classify which is a cat and dog, right? So in this case, we have a color images where we have a red, green, and blue channels. So I want to extract a mean value, which means the sum of all the pixels in the images of red channel and sum of all the pixels in the green channel and then blue channels, right? Sum up and divided by the number of pixels. Similarly, you take the standard deviation. So for each images where we get the 6-dimensional feature vector. So in this case, the row represents the number of sample and the column represents the dimensions of the feature vector. So in this case, when we train the machine learning algorithm with the supervised learning algorithm, where we are given with the input and then output. In this case, inputs are the feature vector, and the outputs are the, for those feature vector, what is the output for those. So in this case, the label and then input feature vector is given. So when it comes to an unsupervised machine learning, where we'll given with the only the input, which means the feature vectors alone, probably we have to group the similar data in this case of clustering, where we can say. So we can group the based on the similarity between the feature vector, where we can group into an n number of clusters. So when we don't have a structured data, which means whether the input is cat or dog, so when such a scenario, you can go for an unsupervised machine learning algorithm to group the data based on the similarity measures. So when it comes to one semi-supervised machine learning, so in this case, some of the data are labeled and some of the data are unlabeled, right? So what we can do based on the structured data, which means in this case, 3 images are already labeled and 3 samples are unlabeled. So we can ask machine to label based on the earlier trained model, which means already machine has the knowledge representation for cat and knowledge representation for the dog. So the remaining 3 samples are unknown. So we can calculate the similarity. They take the second data and compare with the cat, and take the second data and compare with the dog. So which one has the more similarity? So we can compute the Euclidean distance between the cat and then unknown data. And if it is a closer distance means which are closer to 0, then it is a more similar. When the distance values are high, then we call it the more similar, high dissimilarity in this case. So these are some of the machine learning algorithm for unsupervised and then supervised machine learning algorithm. I'll just quickly, I'll go for some of the real-time applications which I want to walk through. So in case of computer vision, when you consider an autonomous car, or it may be an advanced driving assistance systems, right? As I come from the automotive industry, currently I'm working in an automotive industry. So where we are trying to use a computer vision applications for several things to automate. So one of these applications are drowsiness detections. Basically, when the driver drives for a long time, right? He continuously, maybe 1 day or 2 days continuously, if it drives, or it may be more than 10 hours, right? He may feel sleepy, right? So because of drowsiness, there are multiple accidents are happening, right? Several people, what they do, there is a EEG signal data. There is a kind of headset, brainwave interface. You can ask a driver to wear some kind of wearable devices where you can get the EEG signal data, and then you can do a classification. But that they won't feel comfortable when they drive, right? So can we go for without any wearable devices? The best example could be keep some dashboard camera and then capture the faces of the human body faces of the driver, and then try to detect the face images, right? So when you want to detect a drowsy, right, which are the most important factor, which could be the eyes, right? Whether the person is closed his eye or whether the person is opening his eye, right? So in this case, where I have a 68 facial landmark point, but out of those 68 landmark points, my interest would be the left eye and the right eye, where I have a 12 facial landmark point. So once I have this facial landmark point, which I'm going for a mathematical calculation, this is a very initial level demo which I'm going to walk through you. So once I have this facial landmark point, try to compute the distance between the no, horizontal point and then vertical point. Then we'll have a eye aspect ratio. So these are the value. You can see when the eye is open, the aspect ratio value will be the above 0.5. When the eye get closes, then we can say the aspect ratio value comes closer to 0. So what we can do, there may be possibility, there may be blink, right? So we should not generate it's an drowsy, right? But we have to monitor for n seconds, which means 2 seconds. Maybe 1 second we may get 25 frames, or it may be 30 frames. Just monitor continuous 30 frames are eye closed, or 40 frames are eye closed, then generate an alarm saying that the driver is sleepy. But there are certain challenges are there. Let me show you one real time demo. So here I'm using an Anaconda thing to run this application, and I have created the virtual environment to set up this library, all this thing. So now I'm using my own laptop web camera to detect whether the person is sleepy or whether the person is. So in this case, my eye is open and it is trying to detect the eye facial landmark point. You can see when the eye get closes, then it says a drowsy alert, and then I'm blinking, right? So at those time, it won't generate an alert. If I close my eyes for some seconds, then it will say it is a drowsy alert, right? So such a scenario, but in this case, when I turn back, when I tilt my head, right? So such a scenario, what happens? It won't perform well. So as I said, this is an initial level implementation of drowsiness detection applications. There are other alternate way to improve that. So what we can do, we can also try to detect whether the person is yanny kind of stuff. We can try to detect whether the person is feeling sleepy, and also we can put some sensors in the cars. We can also try to take the driving pattern, steering pattern. When the person is feeling sleepy, the steering pattern keep on get changes, right? And also there are possibility of sudden brakes also. You'll try to put some sudden brakes. So we can use multiple information together, and then we'll try to have a robust kind of drowsiness detection systems. So these are other applications demo, especially for the facial emotion recognition. So this can be used for several applications. So the one recently in China, what they did, they used this emotion recognition, especially whether the students are how they are listening the classes, like happiness, whether they're feeling the classes are boring or whether the classes are going well. So they have used a classroom based emotion recognition application to monitor the students' enthusiasm in a classroom activity. So in this case, there is a Kaggle data set, especially for the facial recognition. I have used such a data set to train my deep learning model, and based on that, it can classify what kind of emotion. So in this case, based on this emotion, we can generate a smileys, and also there are some AR and VR augmented reality applications also we can build. Like we can put a there are several applications for the babies, right? When we take a pictures or when we have a, we can put some kind of animations into our face based on the expression. So such things we can do it with the emotion recognition. So let's see the demo for the emotion recognition. So in this case, as I mentioned, there are 6 different types of the emotions are already trained with the machine learning algorithm. But while training the emotions algorithm, I have used only the face images, the cropped face images, and then I have trained. But once we have a trained model, we can do a predictions on the test images. Only the thing is, we have to have a two-steps process in this case. First, we have to detect the face region. Once, then do a face cropping out of that. Once you have the cropped face images, then you pass on to an emotion recognition algorithm, identify whether the cropped face images are happy or whether it's sad or whether it's angry. So we can have a different types of emotion based on the machine learning trained model algorithm. It is capable of classifying whether it's a neutral or whether it's happy or whether it's a sad. So whatever you can train with the 10 different types of emotion, then your algorithm can classify such kind of emotions. I'll just quickly I'll go back to the questions. I may take a few minutes. Is that fine now, or still you people are facing an issues with my audio? Let me check. Is that fine now? Can somebody respond? Is that okay now? Okay, thank you. Can anyone respond? Is that my screen visible? Okay, thank you. So the next applications which I want to discuss about the computer vision, the main thing phone it comes to be done face recognitions, right? For the unlocking of our mobile phone, or it may be a face biometric authentication system which can be deployed for the industry, or it may be any education institution. Most of these China nowadays they integrated. They won't take an attendance for classrooms. They use an face recognition biometric system to capture the each person face images, and then they will put an attendance, right? So in this case, which I want to discuss in face recognition, what are the steps are involved, especially in the face recognition. Let's assume that there is an camera input video stream, and then we get a multiple one by one multiple frames has been read from the camera, and then you try to identify the how many faces are there in the each frame, and then detect and then crop each face images, and then you go for an some feature engineering technique, and then you will be having the registered face images in the database, and then you try to have a comparison between the
the query face images and the registered face images and identify whether the person is known or unknown. So when I say how can we what is the possibility to detect the face images? So in this case, where the structural shape of the pattern. So in this case, you can see on the arrow which I am representing, where we have the human face structural pattern. You create a sub window from the query images, and you try to scan this window across the query images, and you try to match with the already we have a structured pattern, and then you compare with the query images structured pattern, and which location the structure pattern matches, then we'll say there is a possibility in the particular region face images. So these are the again the handcrafted features, but in deep learning currently people are using for the deep learning based face detection algorithm, both for the detection as well as the recognition. So once we have these cropped face images, then we go for an feature engineering technique. Once we have an feature engineering technique, so in this case, let's assume that I have both the person images are same. So I extract a feature pattern, feature engineering technique, a 128 numerical feature engineering pattern, and then I'll take an Euclidean distance. So in this case, I'm getting a distance value of 0.4. So what I'll do, I'll keep a certain threshold value, which means I'll keep a 0.5 as a threshold value, which are less than threshold value. I'll call it as a same person. If it is a greater than the certain threshold value, then I'll say it is a dissimilar person. So where I have in the bottom, where you can see the first row and then second row, first column, both the persons are similar, where we are getting the distance value of 0.2. In the first row, second column, where you compare it is a dissimilar person between the second row, second column, and then first row, second column. So where it is pointing this similar person, the distance value is 0.9. So when both the persons are similar, then we'll say it is a distance values are less. If it is a dissimilar person, then the distance values are high. And one more thing, in face recognition, we'll say identification and then verification. When I say it's a verification in mobile phone, where we'll have only one person is registered and the query is also one, we'll have a one-to-one matching. But when I say it is some industry or some organizations, right, where there will be multiple persons will be working on the industry, right? So there are n person will be registered on the database, and then query will be one, where we'll compare one images with the n person, and then we'll do one recognition. So that way call it an identification. When one-to-one, we'll call it an verification. So let's see some real-time demo for this application, especially on the face recognition. So in this case, already my face image is registered with the database. So I'm trying to identify whether the person is known or whether the person is unknown. So in this case, Some problem. I think there is some issues which I'm facing. I'm not sure if you're able to see. So I was not able to view the window. So though it identifies the person and it tries to tag whether the person is known or unknown. And there are certain issues, especially when it comes to one face recognition. There is a possibility of spoof attacks. Recently, what happens? The iPhone 10 they launched with the face recognition, Face ID technology, but still it was a failure technology because of when I show the printed photograph of the known persons, right? And then the machine is capable, the mobile phone is capable of saying that the person is identified and it get unlocked. And when even there are possibility, we can also have a recorded video stream and show in front of the system, and then it will identify the person is XX. Because most of people, what we do basically, we take a pictures and we post it on the social media, right? But the attackers, what they do, they use those information to attack or spoof your mobile phone, right? So let's see an applications for the especially and the face spoofing attack. So basically we call it as a liveliness detection. So in this case, the liveliness in the sense whether the person is really is in front of the camera or is using some medium to identify the So in this case, already I have trained my model, a deep learning model, where it can classify whether the person is real face images or it is a spoof or fake images. So if it is a real, then we have to go and identify whether the person is X or Y, or else if it is a fake images, which means, so in this case, so when I show some of the, in this case, I'm just trying to show my mobile phone where I have several pictures. It will try to detect, I'm trying to show in front of the camera with my mobile phone, with my face images. And then though it is trying to detect my face images when I show from the other medium devices, right? But that should not happen. That should not identify whether the person is X or Y, because the person is not really in front of the camera. So what I'm trying to say in this case, first step is to identify whether the person is real or fake. Real in the sense the person is in front of the camera. Fake means it is showing some printed photograph or from the mobile phone or some medium is using to spoof the face recognition system. So this was the thing happened on the iPhone 10, but now they solved that issues with the technology, deep learning technology, and so now I think they solved those issues. But still, people can use a 3D mask or silicon when we do a surgery, right? So such a scenario, how far your algorithm can work better. So now I'll go back to the CNN and the neural networks. So I'll talk about what is CNN and neural networks, and then I'll just quickly I'll have a walkthrough on the code as well. So let just take few minutes to take the questions if there are any questions. Can we create a API for ML model in Google Colab using Flask? Okay, may I get the recorded video of this session? See, the Google Colab is a platform. It's a free where they are providing, where we can use the resources. Once you have the trained model, and then you need to create your own instance, right? Until that, you cannot publish as a API. So it's a platform where we'll have we can run our deep learning algorithm with our provided data. So it will not run continuously your instance. There is a limited continuous 12 hours you can use. After that, the session will get restored again. So you cannot host any machine learning or algorithm on the Google Colab. But you have to go for GCP where you can host your the application, the API and the GCP, which is a paid one where you can have those things. But in Google Colab, it's not possible. Just let me have a session. Then we'll have a what is the importance of Google Colab. What are the things can be done using Google Colab? Let's see after this session. So as I said, initially we discussed about the computer vision features, right? Which I talked about, the color feature and the texture features, right? So those are application dependent, which cannot be reused, right? And then once we have a feature engineering technique, then we'll go for a machine learning classifier. Then we'll have a finally then output, right? So basically, as I mentioned, it is an application dependent. We cannot reuse, and also it is an very costly, to develop such handcrafted features. So in case of deep learning, where we provided several samples to the algorithm, where it tries to learn the feature pattern. In this case, we'll have several layers in the deep learning architecture. It may be 100 layer or it may be 1,000 layers. So when I say more than 2 layers, then we call it some deep learning. So that is a term where people call it some deep learning. So in this case, the first layer may extract the edges and corners and shape. Then you pass those features to the next layer where it can get the structural part. So when we reach at the last layer where we'll have a distinct features. But when I consider the first layer, there may be redundant features will be available. But when I reach at the last layer, where it happens the high level features with the distinguish between the different objects. Then finally, we'll try to do one classification. But in earlier case, in traditional approaches, there are 2 steps. First, we get an features, then we go for a classification. But in case of deep learning, where it is an end-to-end system, we'll have a single pipeline where we'll have a feature extraction followed by a classification. So the base for the deep learning is a neural network. So the neurons, it's basically the neural networks came from our human brain system, where we'll have a n number of neurons which are getting interconnected. So in this case, the single neuron receives n number of inputs, and then it does some computation and it passes the output to the next layer. So basically, neural networks where we'll have an input layer and output layer, and then in between we'll have a n number of layers that we call some hidden layers. So basically, the input layer, we can decide the number of neurons, and we can also decide the number of neurons for the output layer. So when I say the input neurons, number of input neurons, if I say 20 cross 20 as my input images, right, which I want to pass through the neural networks. So where I'll have a 400 pixels. Let's assume that I have a 20 cross 20, 400 pixels. So I'll have a 400 neurons. So each neuron will carry the one input pixel value. And probably I want to do a cat and dog classifications, right? So if it is a binary classification, whether it's a cat or not, then we can go ahead with the single neurons at the output layer. If you want to do more than one classification, which are multi-classification, then you need to decide the number of neurons. So the number of classes, if you want to do a 10 different classes, then the number of neurons for the output layer will be the 10 neurons. Then we'll have a hidden layers, which are it may be a hidden layer 1 and hidden layer 2. How many neurons for the hidden layer 1 and how many neurons for the hidden layer? Those are hyperparametric. There is a term called hyperparameter tuning. We can play around with the number of neurons for the hidden layer 1 and hidden layer 2. So we need to see the performance metrics and then look at which number of neurons has produced the better results. So in this case, each neurons carries the input signal and along with the weight value. For example, let's assume that I have a stone or something, right, which I'm passing, which I'm giving the more pressure, then it travels the longer distance, right? So in this case, the pressure is the, I can say it is a weight value. So here each neurons carries the weight signal, where we do a dot product between the input feature and the weight value. And then we sum up there is a 2 neurons which receive the input signal. You just do the dot product between these 2 signal and sum up and then pass on to an activation function. So in this case, basically the activation functions plays an important role because here we are using a non-linearity. So to get the non-linearity, we are going for an activation function. So in this case, there are 3 activation functions. There are more activation functions are available. Sigmoid activation function. So in this case, so once you have the dot product summed up value, it goes to a sigmoidal activation function. So whatever value you get the summed up value, it will be normalized into one 0 to 1 in case of sigmoidal activation function. In case of tan H, it is normalized into one 0 to minus 1 to 1. And the ReLU, it removes the negative value. Only the positive value will be taken, which means I'll be getting minus 20, but it will be normalized to 0. If it is a positive value, it will be taken as it is. So so in this case, the blue neurons, you get the summed up value, you pass on to any of these activation function. So I'll discuss which activation function has to be used in which layer. So that we'll discuss little later. There are in neural network, there are 2 kind of pass. One is the forward propagation and the other one is a backward propagation. So basically in training phase where we'll have both the things, forward pass as well as the backward pass, but in the testing phase only we'll have a forward pass alone. In the backward propagation, basically where we'll trying to reduce the loss, and then by changing the weight value. As I mentioned, each neuron carries an weight value. Those are generated by random value. So the random value cannot classify all the samples, the correct values. So to once you have the predicted value and with the actual value, you will try to calculate the loss. With the calculated loss, you will try to go back and do the weight updation technique. So these are some of the key terms which is used on the while using any deep learning or neural network. So one is an cost function. We'll try to predict some of the input data, and then we'll try to see how far it is closer to your actual value, and then we'll try to reduce the error. As I mentioned, the back propagation where we'll try to do the weight updation and the bias updation. And then the learning rate, it's a constant value, which is an alpha. So we'll try to do a dot product with the gradient value when we do one back propagation. So it basically, the learning rate will be the very smaller. It may take more number of iteration to get the optimal weight value or lesser loss value. So usually the learning rate value should be very smaller. If you have a larger learning rate, it may miss the optimal weight value, but it will take very less number of iteration to get the optimal weight. So the other one is an optimizer. So as I mentioned, the weight updation technique, right? So which algorithm we are going to use to update the weight. So in this case, the stochastic gradient is a basic algorithm, but there are several other versions which are Adam algorithm. So the most used algorithm for the optimization. The other things are regularization. There are 2 things are there. One is an overfitting and then other one is an underfitting. So when we train any of this neural network, we'll be providing several sample data. So where our algorithm or model will have a better understanding on the training data. But when I provide some of the unseen data, the model will not perform well. Then we call it overfitting. So how to avoid such a scenario? So there are terms which are we can use some of the dropout layer or batch normalization in the neural networks, or it may be deep learning. So the other terms which is an epoch, so where how many iterations we are, whether 100 iterations or maybe 1000 epochs. So while the same data will be fed to the n number of times. So quickly I'll just walk through. So here I have an input images where I have a n number of pixels. So each pixel will be reshaped into an 1D vector which pass on to the neural network. So as I mentioned, there is a 2 vector. One is an x vector and other one is a w vector. So you will have a dot product between the x and w vector, and you sum up and pass on to an activation. So this is a simple activation function where we'll have a 1 and 0. So if it is a greater than 0, then I'll call it an 1, or else it is a 0. So in this case, I have 3 neurons at the input layer and binary classification, 1 neurons at the output layer, hidden layer with 2 neurons. So initially we'll be giving only the input neurons. With the input neurons, we have to compute the hidden layers, and then we'll compute the output layer. So in sequential manner, we'll try to compute each of these layers. So in this case, the N4 receives the 3 input signal followed by the weight value. So in this case, the N1 into the particular weight, N2 into the particular weight, and N3. You sum up and F represent the activation function. So whatever the output we get from the activation function, which will be assigned to the N4. Similarly, N5 also receives the same input signal, but the difference are the weight values are different. So similarly, you multiply with the particular weight value and you sum up, pass on to an activation function. So now from the input layer, we computed hidden layer neuron value. What could be the next layer, which is an output layer N6. So the N6 also receives two input signal, followed by an weight value. So you compute the N6 and the output value. So you'll have an actual value and then output neuron value. So you compute the last value, the error. So with respect to error, we'll try to, if the error is it's 0, then the model is learned properly. If it has some value, then we have to reduce that error value, which comes to closer to 0. Then we can stop the training the deep learning or neural networks algorithm. So these are the just steps which are involved. So there are 12,287 pixels are there. Those many neurons at the input layer, and you do a dot product between the double weight vector and the pixel, and then sum up with the bias value, which is an offset, which is a positive or it may be negative. We'll call it as an offset, and then here the ReLU is the activation function, and then finally you get some value from the output layer, and then you compare with the threshold. It's a binary classification. It's a whether it's a cat or not. It's a greater than 0.5, then we call it it's cat. Less than 0.5, it is not a cat at all. This is the other way of representation where they are. So let's assume that I just want to, because we are just assuming that how the neural networks look like, just take some random value and then have a calculation of that. So in this case, I have a one hidden layer with 3 neurons at the input layer and 2 neurons at the output layer. Basically, the input neurons will not do any computation, just pass the value to the next layer in the architecture of the model. So here, to compute the hidden layer value and the output neuron value, I'm going to use the sigmoidal activation function. So let's assume that these are the value which I have taken: 0.5 for the input layer neuron 1, 0.9 and minus 0.3. So now I have hidden layer 1, hidden layer neuron 2, neuron 3, H3. So hidden layer 1, we have 3 neurons, H1 and H2 and H3. So in this case, the H1 also receives 3 input signal, H2, H3, but the different weights are random. These weights are randomly get generated. So we have to, through the training data, by learning algorithm, we'll try to do this weight updation based on the last calculation. And similarly for the O1 and O2 also, there are 2 weights are getting generated. So now let's do a computations of the hidden neurons. H1, so in this case, 0.5 into 1, 0.9 into minus 2, plus minus 0.3 into 2. So you sum up all this value where you get the minus 1.9. As I said, we are going to use a sigmoidal activation function. So here the sigmoidal activation functions are 1 divided by 1 plus exponential of minus t. Now we have the t value, which is a 1.9. You just pass that value minus 1.9 and then probably you'll get 0.13 if you do a computation. Then similarly you go for an H2 neuron, 0.5 into 2 and 0.9 into 1 plus minus 0.3 into minus 4. So you'll get the value of, you'll arrive at the value of 3.1. Similarly, you go back and compute the sigmoidal activation function. So similarly, you compute for the H3. So from the input layer, we were in a position able to compute the hidden neurons value. The next layer in the network is the output layer. So similarly, we'll have a O1 and O2 weight, and similarly, you do a dot product, and you will be able to get the output neurons value, which are 0.35 and 0.85. Just assume that I'm just taking the actual value, which is the ground truth value, which is the T, and the predicted values are O, and the weight value, and these are the I is the input neurons value. So now what basically, as I mentioned in backpropagation, we'll try to compute the gradient value, which is an gradient descent. There is an algorithm called gradient descent, where we'll try to compute the gradient with respect to the error, and then we'll try to do a weight updation. So in this case, my predictions are 0.35 and the actual value is 0.9. Just compute the loss and then take a derivative of that. Then you go back and do the weight updation for all the layers in the network. So this is I'm not just going a detailed way, just to highlight what exactly happened at the backpropagation. So do you have any questions till this? Let's see if any questions on this. Okay. So I'm just going to walk through with the neural networks code. So this code is available on my GitHub repository. My GitHub repository is Mohan Raj MIT. So if you go back and you can look at my repository. So all the codes are available here. Maybe if you want to practice, you can use my repository. And then, so basically, if you want to use the repository from the GitHub in the Google Colab, just go back into the menu, file, open notebook. So there is a tab, GitHub. So you just paste my repository, which repository you want. There is a repository named DL training. These are the IPython notebook files are available. So the one which I'm going to use, MNIST dataset with the neural networks. So initially I imported the necessary libraries, NumPy, Pandas, and here I'm using an Keras library, which is an API where it runs either Theano or it may be TensorFlow or MXNet. But the most used libraries are a TensorFlow as a backend. So in this case, I'm going to use the Keras dataset as a MNIST, where I'm downloading the dataset from the S3 Amazon bucket. So there are 70,000 samples, 60,000 samples for the training, and 10,000 samples for the validation of our trained model. So in this case, each image represents the 28 cross 28, which is a grayscale image, which means only one matrix. So where I'm trying to visualize some random sample in this case. So if you want to run this sample, you need to log in with your Gmail account. So I'm just running each sample here. Once you connect with your Gmail account, and it will say that you are just trying to connect the Google AWS Cloud Google Cloud GPU server. So once it is getting connected, then you can run each cell in the Google Colab. So I'm just trying to randomly, get the trained data. So in this case, I'm the X train of 0, which I'm trying to display, which is a 5, the digits. Let's see what happens at the 10th position. So which is the 3. So just to see what the data are, these are handwritten digits data set. So where we are trying to classify the digits between 0 to 9. So if you write something and if you provide to the machine, which will have a capability of classifying what the test data it is. So and one more thing is that here before training the deep learning model, so we are trying to flatten the 28 cross 28 into an 1D vector, which means I'll have a 60,000 row, and each row represents the 784 pixel value. The column represents the pixel values for the each images. So in this case, 60,000 training data and 10,000. The column values are 784. And so each pixel values are 0 to 255. So in this case, I want to normalize the pixel values between 0 to 1. So to do that, I'm just dividing the pixel value, each pixel value divided by 255, which is the maximum value, so that it will get normalized into 0 to 1. And one more thing, there is a concept called in neural networks or deep learning, we'll call it as an one-hot encoding vector. So basically, machine cannot understand the class label or output value, where we'll say 0 or 1. So for that, we'll convert into a 2D binary representation. For example, in this case, I have a 5, right? So in this case, there are 10 different classes. So I'll have a 10-bit representation of a binary value. So at the 6th position, where I'll have a 1, because I'm starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 till 9. So there will be 10 different binary representation. At the 6th position, where I'm representing it is a 1. So similarly, what you can do, you can based on the number of classes where those many binary representation of bits will be there. Because the machine can understand the binary representation instead of number or string. So whatever your label data, it will convert into one binary representation. So now in this case, where I'm going to create the neural network, so each layer will be stacked sequentially. So here, as I said, the hidden layer will be the dense layer, and then the first hidden layer with the 512 neurons. The hidden layer, there are 512 neurons will be created. For those 512 neurons, what is the input dimension? So in this case, I'll be having a 28 cross 28.
So if I convert into an 1D vector, it will have a 784 neurons. So each neuron will receive the 784 signals, and the activation function, which I'm going to use the ReLU activation function. And then there is a layer called dropout, right? So you would have seen probably all the neurons from I2, from H1 to H2, all the neurons will be getting fully connected. All the neurons will get connected. So can we remove some of the connections? Which means, so in this case, if I have 100 neurons, so randomly I'm going to remove the 20 neurons, right? So to reduce the overfitting or underfitting, as I mentioned, there is a concept called regularizations, right? To avoid the overfitting, people will go for using the dropout layer, where it can remove some of the connections. And the next layer, which I'm going to use hidden layer 2 with the 512 neurons, and the last layer with the output layer with the 10 neurons, because I'm going to do a multi-classification, which I want to do a classification of digits between 0 to 9. So the last layer, we are using a softmax activation function. So in this case, there are two things. One, we can do a binary classification, and other one is an multi-classification. If you want to do an multi-classification, you have to go for an softmax activation function. If it is a binary classification, you have to go for an sigmoidal activation function. So now in this case, just we created a model, empty model alone. So now when we do on back propagations or the model training, we have to specify what is the loss functions we have to use, or what kind of optimization technique we have to use, in which metrics we want the performance metrics. So basically there are two terms in this case of loss. If it is a binary classification, you have to go for a binary cross entropy. If it is a multi-classification, we have to go for a categorical cross entropy. If it is an optimization, which is a weight updation technique, as I mentioned, there is a gradient descent, right? So there is an advanced technique of gradient descent, which we call it as an Adam optimization technique. I just need the metrics in case of accuracy. So in this case, from the training data, I just need, say from the 80,000, 60,000, 80% of the data, I'm going to use it for the training. Remaining, I'm going to use it for the validation of my training data. So in this case, let's train the model. So I'm just going to start the training of my model. So while training the model, we need to specify which is the pixel value. The train X is the pixel value, and the train Y is the output value. For those images, what is the output value, and then number of epochs, and then validation data. There is one more concept called batch size, because in this case where we have a 60,000 data, right? So I cannot feed all these 60,000 data into my RAM, and then I cannot do the computation of loss. Instead of that, take a segment by segments of input data, and then you do the weight updation. So here I'm just starting the training. So one point here you need to monitor. So when at the epochs first iteration, my losses will get reduces when you increase the epochs, and the accuracy will increase and the loss will reduce. If your accuracy is not increasing, and then your training data itself not proper, which means we'll call it an underfit. If your training accuracy is more and validation accuracy is very less, then we'll call this an overfitting. So there are different way where we can avoid this overfitting. As I mentioned, we can use a dropout layer, and you can also play around with the number of neurons at the hidden layer, and then you can play around with the iterations. You can increase the layers in the number of layers in the architectures. Now I trained my model. I just want to, so you can see the accuracy for the training accuracy is 98 and the validation accuracy is 97. So now I'm going to measure the test accuracy, so which comes around 97%. So you can also make a predictions, and you can store this into some file. So if you want to download all these files, where it is available here. So in this case, I'm just making a prediction, and the output of CSV file is available, where you can download and you can see what could be the results actually. So there are two prediction, and actual value and the model predicted result. So the model is predicted 7 is a 7 and the 1 is a 1. So we'll just try to see if any mistakes are happened here. Most of the things are correct, because we got of accuracy of around 97%. So only few data are made mistakes. So you can go. These are the results. Actually, 10,000 samples will be there. So we have used 10,000 samples for the test data where it made a predictions. So let's take a questions. I think there are a few questions. Let's see. So in this case, the fully connected layer or hidden layers are a dense layer. In Keras, the functions we will call it as a dense layer as a fully connected layer. And the stochastic gradient descent is an ADAM is an advanced version of stochastic gradient descent. Let's quickly go back to and have a walkthrough on the CNN. We have around 10 more minutes. I will just take. So in this case, from the MNIST data, where we have given into a neural networks, and then we did a classification of each digits, right? So we are not extracting any features at all. So in convolutional neural network, where it's going to extract the feature pattern and then followed by a classification. So basically the CNN has the three layer. One is a convolution layer, pooling layer, and fully connected layer. So the main importance of the CNN would be the convolution layer, where it's going to extract the feature pattern out of the each input images and pass on to the next layer in the network. So let's see simple architectures for the CNN. So in this case, I have an input image with the bird, and where I have a convolution layer. So basically the convolution in the sense, I'll have a smaller matrix. This is the smaller matrix with a blue rectangular box, where I'm trying to slide that bounding boxes across the input images, and it's trying to scan the feature pattern. There are multiple such bounding boxes will be there. Multiple filters we'll call it the kernels, where the filters are trying to extract the feature pattern, and then you pass on to the next layer. So in this case, the convolution layers are more important in extracting the feature pattern. This is the max pooling layer. Basically, the max pooling layer will have the reduction of the each feature map. And then we'll have a fully connected layer, which is a one-dimensional vector. You just flatten the 2D vector into 1D, and then you will have a n number of neurons in the hidden layer. And finally, you will have an output layer, where each output layer, for example, I'll have a 10 neurons, right? Each will give you the probability, how far it is a bird, and how far it is, which one has the higher probability, that will be the predicted classes. This is another simple architectures where I want to do a classification of whether the given image is cat or not. So in this case, basically, we'll have a several convolution layer and then pooling layer. The rule says that first has to be the convolution layer. You cannot place the pooling layer before the convolution. You can have a subsequent convolution layer, and then you can have a max pooling layer. So in this case, I have a 3 convolution layer and 3 pooling layer, 1 fully connected layer, 1 output layer. You can also see till this max pooling, we call it a feature extraction. And when it comes to a fully connected layer, the right side part which I'm showing, it's a simple neural network. So in earlier case, directly the raw pixel value we fed into a neural networks, and we did a classification. To improve the performance of such a MNIST digit recognition, we are just using a convolution layer to extract the feature pattern, and then pass that into a neural network arc instead of giving the raw data pixel value. So I was talking about convolutions, right? What exactly the convolutions, right? So in convolution layer, just a minute. So in this case, there is a convolution layer. So just assume that this is my input matrix, and then I have 2 different filters. A is one filter and B is the other filter. A filter means where it going to scan my input images and get the shape, or it may be a edges, or it may be corner features. So you are going to scan this filter across my input images. Just slide this kernel, my input pixels across the each pixels in the input images. When you want to fit this kernel into my input pixel, just take the center of the kernel value into an input pixel. For example, in this case, I cannot fit the kernel value into I1 pixel, because when I fit this kernel, it resides the outside the boundary. So basically, when it's a 3x3 filter, we'll skip with the one border across the input images. which means I6, I7 and I10, I11 pixels alone we can do a convolution. So to overcome such a things, there is a concept called zero padding. So we'll pad with the zero so that the input and output matrix from the convolution layer would be the same. But if you don't pad with the zero, then the feature map shape will get reduced. So there are two different filter in the sense there are two different feature pattern where it's going to extract from the input images. So it's going to do a dot product between the input pixel and the filter value, and you sum up the pixel value and place it in the output matrix. So I was talking about the zero padding, right? So in this case, I want to do the convolution at the I1 filter, right? Because when I fit the center of the kernel, A kernel into an I1, then there are 5 pixels which resides outside. So we are padding with the 0. So only we multiply the 4 pixels along with the filter, and then you sum up and then you put it at the output matrix. These are simple calculations how the convolutions happen. So here you have a 7 into 1 plus, and then 4 into 1 plus 3 into 1, then 0 into 2, 0 into 5, and 3 into 0, and minus 1 2 into 3, minus 1 into 3, 2 into, sorry, 2 into minus 1. So you sum up and then you will get a single value here, which is a 6. Similarly, if you move this kernel 1 pixel the next one, which means from 5 we applied the convolution, the next pixel would be the 3. Now you fit the kernel again, you move this kernel till you reach the last pixel from the left to right till you reach at the last pixel, which means 4. So now in this case I have not applied the zero padding. So with the 3 cross 3 kernel, so the output shape could be the 3 cross 3. From 5 cross 5, the convolution layer output could be the 3 cross 3. So when, for example, when I say I have a input images of 32 cross 32, and then I have a color images which are a 3-channel matrix, where I have a red channel, green channel, and blue channel. Each matrix has the 32 cross 32 dimension, and then I have the filter size of 3 cross 3. And then there is a one more dimension because we have a depth as a 3. The input depth is 3. So the filter size also will be the 3. There are different dimensions of filters we can have, either 5 cross 5 or it may be 7 cross 7. But most preferred used filters values are 3 cross 3, where it can capture the detailed information. So in this case, these are the 5 cross 5 is the filter size, height and width of the filter size, and the third is the input depth. So in this case, I have a input depth of 3, and my filter depth is also 3. So now, as I said here, I'm not going to use the zero padding. If you don't use the zero padding with the 3 cross 3 kernel, the one border of the one row, first row, last row will be skipped, and the first column and the last column will be skipped. There are 2 rows and 2 columns will be skipped, so the output will be the 30 cross 30. So I have used 3 cross 3 filters. So I got one 30 cross 30 feature map. If I'll have a multiple feature map, which means I'm going to use 32 different filter of 3 cross 3. I'll have a 30 different feature map, maybe edge and corner. So each feature map are getting stacked on top of the each others. So this is the mathematical representation for the to compute if I'm passing some input data, and then I'm going to do a convolutions layer, right? Let's assume that my input data is 32, right? So either it may be height or width. So 32, my filter size is 3. So 32 minus 3, and whether I'm going to use a zero padding or not. Let's assume that I'm not going to use a zero padding. My p value is 0. So 32 minus 3, it becomes 29. And the style value, how many pixels we are going to move the kernel value or the filter value, which is called as the style, which is a 1. So 29 divided by 1 plus 1, so it becomes 30. So if you don't use zero padding, and if you use the 3 cross 3 filters for the input dimensions of 32 cross 32, the output will be the 30 cross 30. Let's assume that I'm going to use a zero padding. P value is not 0. P is equal to f minus 1 divided by 2. So in this case, the filter size are 3. 3 minus 1 divided by 2. So it becomes 1. So 32 minus 3 plus 2 into 1. So it becomes 29 plus 2. So it becomes 31 divided by 1. So it becomes 32. So with this formula, we can compute what could be the output feature map from the convolution layer. So when I have a 5 cross 5 kernel, so there will be so in this case, I'm going to use a 5 cross 5 kernel. So I'm padding 2 zeros, I'm padding with the corners. If it is a 3 cross 0, only one 0 if you pad with the corners, that is sufficient. So it depends on the what kind of filter dimensions we are going to use. This is a simple example how the CNN learns the features. But in this case, the first layer, the ear features and the eyes are extracted. And then in this case, the leg features are extracted. But when at the second layer, the eyes and ear features are combined. And in this case, the leg features. So when you arrive at the last layer, which are third layer, it will have the whole structural shape of the cat. But in case of the first layer, each will have the different. First layer, the shape feature, for example, ear feature will have independent, nose will be the different. But in case of the last layer, all the features are combined. In this case, the eyes and ears are combined at the second layer. In this case, the leg features are combined at the second layer, and the third layer, all these features are combined, so that it will have a proper shape of the cat. This is a simple example how the car has been passed across all the layer, and when it reaches at the last layer, the probability score for the cars is high. The next layer, which is a max pooling layer, as I said, the max pooling layer, we are going to have the reduced dimension of the input feature map. So for example, let's assume that this is the input feature map which I'm getting for the max pooling layer. Here the kernel size are 2 cross 2, where we'll have a 4 pixel value. So in earlier case in convolution, where we do a dot product between the filter value and the pixel value. But here just we are going to do the pixel test within this filter, which are 4 pixel, which one has the maximum value. And also in earlier case, where we use the stride value is 1 pixel, we just move across the each pixel. But in this case, we are moving the filter non-overlapping fashion, which means in this case the pixel stride value is 2, which I am applying for the 7th pixel. The next pixel would be the 5. So within these 4 pixel, which one has the maximum value? So here we are sliding the kernel in a non-overlapping fashion. So in this case, from the 4 cross 4, the output feature map from the max pooling layer is a 2 cross 2. So max in the sense which one has the maximum value out of the 4 pixel, that we call. There is the other way also, where we can get the average pooling layer, take these 4 pixel value and take an average out of that. But the most used approaches in the preferred approaches which gives the better performance is the max pooling layer. So I'm just left with the demo of CNN, then I'll go back to the questions. Just I'm going to run all the cells. So only the difference between the neural networks and the CNN. So here I just added the convolution layer. Before I go into hidden layer, I have added 2 convolution layer and 1 max pooling layer. So first I'm using a 32 different filter, and each filter sizes are 3 cross 3. And then I'm using one more convolution layer with 64 different filter, and each filter sizes are 3 cross 3. And then max pooling layer with the filter size of 2 cross 2. And then I'm just doing a flattening of what are the output which I get into an 1D vector. And then dense layer, which are hidden layer with 128 neuron. And the last layer with the 10 neurons, which are the max pooling layer. So here you can see what I have given 28 cross 28 and 32 different filter, and each filter size is 3 cross 3. So you can see the output feature, because I'm not using a 0 padding, the output feature map get reduced into one first row, last row. So 2 rows, 2 column has gone. So it become reduced into 26 cross 26. I use the 32 different filter. Each filter will give you 26 cross 26. So it becomes 32 different 26 cross 26. Then I use the 64 different filter. Again, it is reduced to 2 rows, 2 column because I'm not using zero padding. As I mentioned, max pooling layer will reduce the feature dimension half of the input feature map. It won't reduce on the depth, only the height and width of the feature map will get reduced. So now I trained my model. Earlier we got around the validation accuracy around 97, but when I used convolution CNN, the same data with the convolution layer, where I was able to get 99% of accuracy. But only the thing is, in earlier case where we passed the raw pixel intensity, but in this case we used a convolution layer where we extracted some of the pattern. From those pattern where we have given to a hidden layer and followed by an output layer, where we got a better accuracy. So I'm just done with my demo. So let's go back and see if there is any questions. See, the third layer, which is a fully connected layer, which are similar to the hidden layer. The only the addition to the neural network in the CNN are convolution layer and fully max pooling layer. These are the two different things newly added to the CNN. But the third one is a fully connected layer, which are a dense layer, or we call it the hidden layer. So that is similar to the neural network. Only the convolution and then max pooling layers are newly added. So I think few were asked about what is convolution and how the feature are extracted. Let's go back and just I'll just try to share my screen. I'll just have a visual representation. I'm just sharing my screen. Let's just have a this is a color image. Let's assume that this is my input matrix. This is for the red channel and green channel and blue channel. There are two different filter W0 and filter W1. Basically, the filters are here. They randomly get generated the weight value. How we generated the random weights for the neural network. Similarly, we are trying to generate the weight value for the filter as well. But in case of traditional way, the filters are fixed. But in case of deep learning, where we are trying to learn this filter value, initially we'll generate with the random, but having through a backpropagation by the learning of deep learning architectures, where we'll have this robust filter value. Basically, these filters are trying to scan this feature pattern where it will extract the edges and shape kind of stuff. So in this case, I'm just sliding this kernel where it is scanning the feature pattern. While scanning the feature pattern, we'll have a dot product between this actual pixel value followed by the filter and sum up and put it at the output matrix. And then here the start value of 2 where we are moving the pixel value. But usually the way of moving the filter value could be the 1 pixel after other. I just want to show you some people asked about what exactly the convolution does. Let me show you one simple example here. So here I is my input image, which is a matrix, and dx is my filter value. So when I do a dot product between the filter value and the I, this is the output which I'll get from the convolution. So this is my original image. For the original image, the output which I get from the convolution layer would be this is the one. So you will not use the same filter. You will have a n number of such a filter, but those filters are not defined. Initially, we'll do a random generation, but those filters value will get changed, keep on based on the learning iterations. Let's see, is there any questions? Even CNN also we have to use an back propagation algorithm. See, every deep learning algorithm, because we are given the input and the output, based on that random generated weight, the model will predict something, and based on that error calculation, we have to go back and do a weight updations. So in this case, as I mentioned here, I'm going to use a 32 different filter. So the depth will be the 32 different feature map, but my input shape is 32 cross 32. So when I use 3 cross as a filters, right? So when we use a 3 cross 3 as a filter, one border of input images, let's assume that this is my input matrix, right? So the one border I cannot apply the convolutions at all. Because how do you want to fit the kernel? We'll take the center of this kernel and then we'll fit into one input images. For example, A is my filter and B is the other filter. So I need to fit my kernel, center of my kernel into an input pixel. If I fit this A kernel into an I1, then A1, A4, A5, A7, A2, A3, which resides outside my boundary. So I cannot apply the convolutions at all when my without zero padding. So I cannot do the one border of the input images at all. So the output matrix would be the from 4 cross 4, only I'll get the 2 cross 2. So if that case 32 cross 32 as my input feature, input data, and if you use a 3 cross 3 kernel, then we'll get 30 cross 30 as my output feature now. What happened? Hello.
Hi, Manraj.
I think I thought I got dropped, I guess.
Sorry?
No, is that connected or?
Yes, I can hear you.
Okay.
But your screen is not shared.
Okay.
Okay. Yes. I was saying if we are good with the whole talk, then we can open up for Q&A session for about 5 more minutes. And
Yeah, sure. I think some of them asked about how to deploy. So what you can do, you can write a Lambda services on the AWS, and then you can deploy your API or whatever you want. So basically, we create some VM instances, and then we either you can do a creating VM instance or you can do a Lambda API whenever it is required.
That's great. Is there, if you want to scroll on top and just check if you've missed on any question, you can, or if everybody, please feel free to drop your question right now if it's missed at the beginning, so that it's easier for Mohan to respond to it. So I think Saurabh's and you've already answered Saurabh's question as well as the back propagation question, if I'm not wrong. That's Murugan's question. Also, something about the third layer is also discussed, if I'm not wrong. So that's
yes.
I think major of the questions, I think Murugan has also asked 2 more on feature and MT, CNN. So I think most of them are answered, no doubt. And Gaurav asked about deploying. So I think Ritesh asked about how to break CAPTCHA using object detection. So that's done as well.
What, Varsha? Couldn't get
The
you.
question Ritesh has asked is how to break CAPTCHA using object detection.
Is there time to just quickly I can walk through what is object detection?
No, so if this question can be answered in the next 5 minutes, yeah, why not?
Okay. Okay.
If he's okay, there is a new question though, if you want to have a look. Murugan is asking how to do video analysis. So I think in the next 5 minutes, you can wrap up here. Thank you.
Okay. See the difference between the classification and the object detection. I'm just giving the general perspective, the difference between the classification and then object detection. When I say image classification, given with the input sample, the model will has the capable of saying whether the given input image is whether cat or dog with the probability scores, right? So in this case, with the probability saying that dog is 99%, 1% it is a cat. So now model is capable of giving only the classification label, but it will not give you the which region the cat dog is belongs to, right? So to get the along with the class label, along with the regions, probably we'll go for an object detection. So in this case, both will have a label and then which region the cat or dog it is present. So the combination of classification and localization, we'll call it an object detection. So basically, when I want to do one object detection, I'll create a window kind of stuff where I'll slide the window across the images. So in this case, instead of doing the image classification once, we are going to do a multiple levels of classification. At each regions of window, we'll try to do one classification. So at each window, try to extract a features and then you do a classifications. Similarly, you move that. So when whichever window it is matching with our target object, then we'll say there is a object is found. So how to break the CAPTCHA using object detection technique? So basically what you can do, the object detection technique, basically you need to do annotation basically. For the object detection, we have to manually put a bounding box saying that this region is A and this region is B. Manually you have to label all the training sample and then you do